All right. Round two. Mic check. Mike. Mike. Michael. Mr. Mike. Microphone. Michael. All right, we're good. Get your coffee, folks. This one's gonna be a doozy. So, microphone didn't turn on the first time. I just woke up, so that's my excuse. However, get ready for this one. I had a student, uh, have a student, and she went through this problem, which I'm gonna give you a peek real quick. Just because we went through it in the recorded session where my microphone wasn't working, we're going to go over potentially, and as mentioned, if a teacher was Bowser and they try to send out the worst troop at the student and make it look like, oh, it's just a tiny little turtle, and the student Mario goes up to the turtle and then it just morphs into this giant mutated monster, this would be the problem. This would be the problem. Because what you're seeing here, it looks like a bunch of gibberish. We're going to do a lot of details, and it might take quite some time actually. But this one little section here, in fact, this little problem right here on the left side, this little piece right here, that's the problem. And then it morphed, and I went to the mutated turtle. And then it wasn't even done there. Then it turns out this mutated turtle was Bowser. All right. So that's the bird's eye view. Now we're going to zoom in and see what the heck happened. All right. All right. Microphone again working? Okay, good. I don't want to start a whole thing and then have to be like, all right, forget it. I'll do it on round three. I'm also waking up slowly. Just made my coffee, so you're going to see me sipping on it real quick here and there. Oh, a sweet nectar of energy that slowly moves its way to the brain. All right. So what we're dealing with here is a proportional comparison. The easier of the types is you have triangles. In fact, these are a little bit obfuscated triangles. I didn't really get the other parts, but the easier types that are similar to this, it's within the same sector of problems that you'll find, but they always introduce them together because if you have proportional triangles, you have some sides of a big triangle and then some sides of a tinier triangle. And you can say they have congruency, similarity between them. Then there's a couple of things we can work with. Normally, we'll maybe have a number for A, a number for C, a number and nothing for B. Imagine B is just a location, but B is not going to be filled in with anything. Then you got a number for, I don't know, A here, and maybe X down here. So instead of a number for C, we have an X value. So if I was to kind of simplify the messiness, just remove those letters initially. You would see a problem like this. And then they'd say, all right, find the actual missing piece, the X of the sides, considering congruency between the two triangles. Well, proportionally, we can think of them as a scaled model. We can have a smaller model, but when we make a small house out of Legos, we can technically convert inches to feet and then create a bigger model that's an actual house, which is pretty cool. Modeling is a common thing we do when we want to create something before we construct it, like small little model, right? Now, an inch to a foot will be a times 12 model. So that would mean one smaller model might be the one value or the initial value, and then your bigger actual model might be a times 12, a blow up of times 12, multiplication of 12. That's just an example. For this one, the way we start the previous problem is through these proportional frames. The first thing we would do, grab a side and notice the slants will be of the same part of the triangle. So 5 and 3, and 7 and x. Second, make sure you adjust them or place them on our proportions in a couple of ways. First, it's the part for part. So hypotenuse to hypotenuse, those are the red numbers on the numerator. Then it's the leg to leg, so 7 to x. Those are going to be across from each other. So hypotenuse across from each other, legs. Hold on a second. Yeah, and legs across from each other. The next thing to really take into mind, which is probably, well, this is the more important part, I would say. You want to make sure that your corresponding comparisons are on the same side of the fraction for both the top numerator and the bottom denominators. The second thing to keep in mind is that we're using the same triangle on the left side. So this is the left triangle. And then we have the same triangle on the right side. So there's kind of like a tops match, sides match. Cool. The tops are going to be based on the location of those numbers, hypotenuse to hypotenuse, leg to leg. And then the equal sign separates the two triangles. So you're really just thinking of it as, hey, set them equal. And in the process of setting them equal, build a proportion to match each side. Perfecto. So we chose to put 5, 3, 7, and x. In fact, we can choose multiple ways. I'm going to do it a different way because I'm going to save an extra set of moments of time. I'm actually going to do 7x because there's no particular reason we have x at the bottom and the 7 at the bottom. I just started from the top left to the bottom right. But if I move my x to the top, I also have to move the 7 from the denominator to the numerator. What that does is just kind of simplify math for me a little bit. In this case, it's not a crazy simplification, but for the next one, that one still will be a little messy. The case is that if you have a big denominator that's really ugly, it's best to move it to the top just to have less writing. So now we're at a point where we're set to find this missing piece, the piece of the proportion of this smaller triangle. Now, applicably, this is actually a pretty cool little technique. So if you have like a skyscraper and you have a tree, that's not a skyscraper, that's just some story building. And then you're over here, and you know that from here, from you to the tree, let's call it 20 meters. The tree is about 10 meters. And then you also know that from you to the building is 100 meters. Well, you know what you can do from here? You're building triangles, man. So your eyesight here to here, give or take, as long as the tree matches the top and the top of the building also matches. So I gotta kind of make my tree a little bit. No! Bigger. Go back. Maybe I'll make my tree a little bit bigger because you gotta have to make sure both of those match each other. So there's my tree. I've artificially grew it to be bigger. So the top of the tree hits the top of the building, and then your eyesight catches that. Well, then with this process, you can figure out how tall that building is. For real, using this proportional process. Because you're essentially building a triangle. Let me make it look like a building. There's your windows. And Of course, welcome to modern commercialism. It's your business building. So you're able to essentially take just the distances that you can measure, the top of a tree and the distance you walk, and you can adjust that because you're a variable, right? You can walk wherever you want. So if you find a point where that tree is hitting that exact part of the roof, the top of the building, and then from that point, you measure how many steps it takes to get to the tree. And I guess you kind of have to climb the tree and measure it in some form. You could probably do it with a drone or an app or something. Probably a drone or a couple of meter sticks tied together. Get creative. But once you find out the tree size, height, and then the distance you are from that tree at the point where the tip of the tree is actually touching the tip of the building, then you can find the missing height of that actual building without having to, I guess, have a bunch of meter sticks floating in midair or whatever other method. So it's a pretty cool method, and it's a form of the similar proportional triangles. Anyway, as far as applicable, that's what that is. We're just doing some basic math here. So what we will do is we're going to multiply 5 to both sides. This side cancels, right side stays. Going to multiply 3 to both sides. Actually, I don't need to do the 5. Shortcuts. I'm still sleepy. The 5's already on the left. Why care? Why care? We just want x by itself, so we just multiply 3 on one side. There we go. Now x is by itself. See? This makes a difference between a student doing extra work and taking extra time to make a test workout and then spending extra time wasted versus just doing one thing. So get some sleep for a test, yeah? I just woke up. I'm still processing my coffee. Anyway, 7, 3 to 21, 5, x. And this is going to be 4.2. So this is going to be about a 4.2 meters or whatever value, because I haven't really designated any particular measurements to these angles or these sides. But this is the format we're looking for. This is the process we want to take. It just turns into a monster. So I had to kind of give this to the side to show what the focus is for the problem we're about to go through. This is just the what do you call those? The mini boss. This is the mini boss right here. We just went through the checkpoint, game saved, we found some extra health potions, and we're finding a lot more health potions and ammo. And we're like, uh-oh, something's coming up. And there's now a save point, and there's a big door, and now we open the door, and we got this boss battle right here. So in a similar fashion, we're still comparing proportions. This is why proportions are so cool. I'm nerding out a little bit. When you have proportions, you can essentially find the heights of buildings using trees, knowing a couple of measurements in between. You can also do this with matching factors. The piece that we want to really pay attention here is the fact that we have parallel lines. All these 3 lines are straightforward, parallel, never going to touch each other, no matter how far we go to the right. They're just going to keep being parallel. So that's kind of an important factor for us to recall here. The second is that this other line going through the parallel and this one, they are a single segment. They're a single segment coming through, and they're very consistent. They're not changing direction. They're not like breaking off and then going this way. Just a straight single segment, or well, line because we have the arrows at the end. With those factors together, we are still using proportions. This is where it gets fun. We're using proportions that are gonna get very, very, very messy. And WTF for sure. God, why is this green happening? Should I put this light on? Oh, that's nice. Okay. That removes the green. I'm still working on green screen stuff. I'm not good at that streaming thing. All right, so we now do a similar factor here where we're comparing Basically two shapes. Polynomials, think of it this way. Before we had triangles, now we have this sort of four-sided polynomial. It's not a square, it's just an odd shape. But we have two of them, and that's kind of the interesting part here. So one of them is going to be located right here because of the parallel lines there. And the other one, just like the triangles, was a bigger version of the smaller. Right, so ignore all the arrows going everywhere. It's a little extra confusing, but when you see that it's one shape proportionally made bigger to another shape, it's a lot more straightforward to look at than looking at all the lines and arrows going everywhere. Sorry, I had to clear my throat. So that just means we're basically doing the same thing. We've got two shapes in comparisons, in proportional comparison as well. So we're going to take, we can do it a couple of ways. I can say, all right, 12 and x minus 2 to keep the same shape on the same side of the fraction. And then 3, this is a fat 3, 3x minus 1, 24 on the right side, keeping the shapes across the equal sign proportion, but also making sure that what this 12 is representing the slanted side. So there's 12 and there's the slanted side. And then the x minus 2 is more of the straight up side, x minus 2 and a 24 still matching. So that's just a check we can mentally do, or we can build it that way from the get-go, and that's what I've done. But if you're not too sure, just remember, focus on the shape on one side, so shape 1, and then shape 2. And then based on shape 1 and shape 2, the corresponding sides too, they have to match. Um, this would be a problem if we built the fraction like this. Because now we're mixing this 5 with this x, which are two different sides of the shape, and yet we're connecting them on the numerator. This would be incorrect and will basically cause you to have the wrong answer. So always making sure the alignment is nice on both shapes, left and right, proportions, and then the actual sides you're focusing on. All right, next up. This is where it gets crazy. So we go from, at first I was like, oh, no way, they gave you this problem. Is this a mistake? Did I do something wrong? And she's like, nope, this is the problem. And I'm like, okay. She's a new student too, so I'm not sure what she's used to seeing, at least with me. She's a new student of mine. And then we realized, yeah, she does know factoring. She does know the AC method, and she does do polynomials. It was just too much. There's a lot at once. And that's what we're going to be going through. Polynomial factoring, especially. But I'm going to give you one of the best methods to factor. I've had so many teachers say, oh, the AC method is so easy. Just take the first number out and make it easier. Oh, if you do it this other way with the thing and the crossing and you guess these, and if they go to the that and the this, I don't like guessing. I don't like guessing. There's only one case I like guessing, and it's if something is in front of me and I can start playing with combinations. And that's what we're going to do. We're going to do factoring in a completely tangible manner. No guessing, no, maybe if these two work together, and then trying to figure out if they don't, the other two to work together, none of that. Those are just time wasters. And when problems get difficult like this, guessing is going to be the last thing you want to do. So the next step would be multiplying both sides by the denominators, getting them out of the way. X minus 2 goes to the top right. 24 will end up being on the top left. Similar groupings cancel, so they go away. And then I was like, oh no, oh no. Not only we got some big numbers, The right side is gonna give me a polynomial x to the power of 2. Yikes. But hey, we're gonna find out the easy way to do these. Now, the next technical step we call foiling. I hate foiling too. First, outer, inner, last. It just makes no fluid form for me. Let me draw what that looks like. First, outer, inner, last. It just looks like lines everywhere to me. Someone's like, oh, it looks like a smiley face. Some teachers will say, look, it looks like a smiley face. Let's make math fun. No, no. The point of foiling is to combine four objects in every possible combination. You have 3x, you have 1. Actually, we'll go with this. We'll go 3x. We have 1 on the left. So those are two terms in one parenthesis. And we can easily see there's two more terms on the right side. So if I wanted to combine everything in every possible way, I just have to make sure 3x combines with x, 3x combines with 2. Why is it stopping here? Come on. That's the first set of combos. Two things, and you give one of them to both. Now we have the other combinations. And isn't that so much neater? All we're doing is trying to combine and mix everything that can possibly be mixed without double mixing and without forgetting about one. So forget about foil if it's too much of a thing to you. I never used it. I actually used foil for so long and it gave me so many problems. I had to figure this part on my own. And that made me basically stop making any sort of error personally. But I've also noticed many students prefer to see it straightforward. Don't give any sort of, oh, look, math is happy. Look, a smiley face. Like that just not, it just obfuscates the information behind. Anyway, you can tell that I'm not very happy with public education. So, this is basically your foiling. So, we're going to call it foil, but we're going to really think of it this way. Just the first pieces that combine. This the problem here is when you forget to do something like maybe the x times x. 3x times x would be 3x squared. Then you get 3x times negative 2 would be minus 6x. Then I got to double check because I'm still waking up and I'm just making sure my math is not going to break here. 3, 2, negative 6x stays. Okay, cool. The worst thing to do math is when you just woke up. I literally just woke up like 30 minutes ago. 15:30, and I just had it in my head and I'm like, I'm just going to record this because I just did it last night and I need to make sure it goes out. All right. Negative 1x. Yes. Okay. So negative 1 and the x combined multiply. Now remember, they're multiplying because as we essentially move between these two sides with these two colored red and green arcs, we're passing through multiplication. So that operation is going to essentially drag the multiplier with it. 3x and nope, 1, negative 1, and x, negative x, and then negative 1 times negative 2 is positive 2. There's some tips on that too, but I think that's for another section there. Multiplying two negatives, one positive, one negative, all that jazz. And this is where I didn't like this process now. So as soon as I was like, oh, okay, it's a factoring problem. Great. But then I'm like, okay, we've got the polynomial. Great. Why is it not working for me? This calculator is broken. Microsoft sucks. Unavailable. Okay, I guess just remove it then. Microsoft breaking. So this was actually some value that was a little bit I'm gonna have to grab my Wabbit emulator calculator. 24 times 12. I'll have to copy my files over. So the left side, 288. That's what we're looking for. At least that's the multiplier here, and it's like, oh, geez, that's a big number to try and factor with. Considering now if we subtract it from this side, Uh, what am I doing? Math forward without doing the math right? 288 and minus 288. I didn't combine these two. That's negative 7x, 3x squared. And then the movement of 1 to this side cancels to 0. Now, this was also a thing I have to mention. If we have a single x, meaning there's no actual power, then we're used to getting x by itself, meaning get x to one side and everything else to the other side. And that'll give you a format of x equals to blah, whatever it's equal to, at least whatever the math ends up being. And when we have the x equal to situation is when we know we're done because it's actually telling us x is equal to 5. It's the same thing, right? It's x is 5. And once we get to that point, we know the answer. However, when we have these squares, we have to adjust a little bit. And that adjustment is we can't get x by itself yet. So we got to place everything on one side, remove everything from the left so it actually is a 0. And here's our final piece here. 2 minus 288 minus 286. Yeah, this is what we're factoring. And if you know where we're going, you know the WTF is popping up somewhere around now. What's the formula? So, there's a couple of things we can start with. And it's not going to be guessing to find out which two numbers are going to combine or multiply to 286 with 3 to get the 7, and then just think about it in midair. The first is we're going to take a factor tree. This is always the situation. And then after we find those numbers, we'll go into group factoring. But at least we're going to have guidance that's not going to be guesswork. We're not going to just stare at this and then get the two parentheses and just be like, The problem here too is that the 3 doesn't really come out. One of the nicer things that could have happened is if this was something that this had. So if instead of a 7, we had a 9. And then I think 286 might actually 286 divided by 3. No, that still doesn't work. So 286 still doesn't have a 3 in it. So if all three of these terms were divisible by 3, then we could have taken the 3 out, would have simplified our life dramatically. Okay, why are we here? However, it's not the case. It's far from the case. The case is on the other side. Oh, sorry. The case is in the other castle. Your princess is in the other castle. This one is a little bit extra. So the beginning is always going to be, all right, AC method, we know this. A meaning the first part of our equation. B is the middle, we kind of use it. And the C is the last part. And AC, because there's no operation in between the A and the C, we just consider that multiplication, which means 3 times 286. Don't multiply. Just put them next to each other. Best way to start this. Because, yeah, you can be a perfectionist and say, all right, well, what's 3 times 286? 858. But then you're going to have to take it apart for the next step. It's always the factor tree we're interested in. The beautiful part is we already got 2 parts of the factor of 858. It's 3 times 286. So sometimes it's better just to let it look like it's about to multiply, but not let it multiply. Just keep it that way. Then the next step would be nice. We can take this apart into 2 pieces by normally dividing by 2 until we can't, basically. So here, divided by 2 is going to be 143 times 2. And this one's a bit more tricky because now you're like, all right, we got some nice numbers. We got a 2 times a 3. And then what can we factor 143 with? You can try a bunch of numbers. 7, maybe it looks decent. I like odd numbers with 7. It's not a 5, so you can ignore 5. It's not a 0, so you can ignore 10. It's not even, so 2, 4, 6, and 8 are gone. 3 maybe. But in reality, it's the only choices you can really test is 3 and 7. Until you realize, wait a second, I can go beyond 10, 11. So dividing by 11 actually shows you that this is kind of one of those weird rules. When we do 11 times 11, anything above the 10 value, it's 121. And this is where the front number plus the back number makes the middle number. The front number plus the back number makes the middle number. It's just a weird pattern with multiplication of 11. Um, Always? Not always. 13, 143. Oh, yeah, that's the one we're looking at. So 13 times 11. And then we can add this or multiply the rest of the numbers. And what we found right now out of the factor tree, you can call them the prime factors if you want. The prime factors of 858. This is the factor tree. And I like to think of the bottom as something different. This is the DNA of the particular number 858. Those pieces exist inside of 858 multiplied. And you can move them around as you wish. It's always going to end up being 858 when you put all of them together into a single. Now, the nice thing about DNA is you can also play around with it. You can splice it up into pieces, see what happens. The first one we can do potentially is let's put the 2 with the 11 and the 3 with the 13. We're not going to multiply the 4 together because we know we're going to get 858. Once we get to this splicing process here, our interest all breaks down to the -7 in the middle. Because we've currently combined the outsides of the equation here. So we're going to basically start dipping into the middle and trying to see if we can find a relationship between the beginning, A, the ending, C, which for some reason decided to not drop down with us, and then the middle, B. When we find those specific little key lock combinations, trying to lock, what is it? Not lock pick, but the master locks. You're like moving the little thing to the left and moving it to the right. Like, come on, make a click, make a click. We're looking for that click. Trying to find that specific number or sets of numbers that'll open up this lock for us. Yeah, but we're actually testing. We're not guessing at this point. We've got a set of digits. Once you find the DNA, you just have to move and shift them around. You already have the numbers you need. You don't have to think about, oh, what number now? 858. Oh, that's such a big number. What two numbers? What can I multiply to get if 858? And then you end up staying in your head for another 10 minutes until the test runs out of time. So in this way, at least we have some numerical playthrough. So, all right, 2 and 11, that's 22, then it's 39. Plus or minus is the case where we're testing now. 22 plus 39, way too big, not going to be 7 off the bat. But if we subtract them, that's still going to be 17. So, no, does not work. But it's close, right? It's very close. It has a 7 in it, so why not just use that one? No, because it's not going to work. However, that's how we test and say, all right, this combination did not work. This lock combination did not work. But I'm so close, I just need to flip two very similar numbers. I'm going to keep the 2 here, but I'm going to give 2 the 13 this time. I'm going to keep the 3 here, and I'm going to give the 3 the 11 this time. So all I've really done is just flip these guys backwards, or I've given it to the other pieces. If the first combination didn't work, now we test the second combination. Boom. So that's going to be 26 and 33. Plus minus to check. Adding them obviously is going to be too big, 59. That's not 7. Back to that middle part where we're trying to find the 3-lock combination. We found the 2 pieces now. The first A and C, but we're looking for the B combination, the third piece to our lock. But the plus is not going to cut it. However, 33 minus 26, 26 to 30 is 4, and then 3 more to 33, that's 7. Bingo. We found the lock. And we got to give and make sure that the 33 stays with the negative stays with the 33 because it's the bigger number, and we do have a negative 7. So I'm just going to give that negative 33 and 7. So boom. Now we've mixed all the digits, all the numbers, in a single combinational factor, and we found how we can take apart this equation and do the next step. Deep breath. Good checkpoint. This is maybe like the first version of the boss before he morphs into like triple the power points. Because the next part's gonna get hefty. At the least, we can say we've gotten to this point. We found 2 digits that are going to give me negative 7. Now in math, we do a lot of tricks, a lot of magic tricks. Probably mentioned it before, but I'll mention it again. We can take a 0 and split it into 2 plus or minus 2 plus 2. Isn't that equal to 0? We can put a 0 anyway, really. I can put a 0 right at the end of 7 and call this. Then I can also say negative 7 is also equal to 2 minus 2. I can do it at any point in time that I wish. It's just better when you do it strategically. There's no point in doing it here. But that's kind of the factor we're thinking about. We can always split numbers in multiple ways. So having that instinct that one number can actually be a representation of 2 different numbers in addition subtraction. Or as we did originally, hey, no, okay, highlight multiplication. You can see 858 as its own single digit, or you can also see it as 3 times 286. Heck, you can even so far as see a single digit as its full primal DNA, right? So there's so many different ways we can essentially mathify something that may not ever exist and pop up with something that is like, all right, I guess it makes sense. It's 2 minus 2 is 0, so cool. Why? Well, teachers are going to do this very often. And many times teachers will skip steps because they assume that you've already figured it. So then all of a sudden you have a number pop out of somewhere and you're like, wait a second, that number wasn't there before, but where did it come from? Help teach, help. Some teachers will be nice enough to explain again and again and again because you're listening now because you're like, oh, whoa, but someone else in the class is still staring at the ceiling. And then he's going to ask the question later again. And then we're going to go through the whole thing again. So, yeah, I understand both perspectives. Some teachers will not want to repeat themselves over and over, but it's helpful to do so. Even if you already understand it, to see it over and over. Repetition is where it's at. That's what helps us learn. So, while it's not really necessary for us to basically have a 0 here, just negative 7, the split is what we're focusing on. The split just basically means if I can split a 0, I can also split a regular digit. And we just found 2 possible digits to split into the 7. That was the whole point of the process here. We wanted to take some numbers, split them, or add them to get the negative 7 so we can find some options for us to basically even out the whole equation. The equation of the 0 here. So what I'm going to do personally, because it doesn't matter which way you split it, there's an easier way and a difficult way. I'm going to do the easy way. Because I see 33, I'm going to scoot the 33 next to the 3. And the 26, because the other one has a 6 and it's even. I'm going to squeeze the 26x next to the 286. That's a positive 26. So why did I put an x there when we were basically just doing a negative 7 with some basic numbers? Well, because, yeah, we didn't include the fact that the original had an x. It's a type x. So we got to make sure the x follows through. The numbers are good. They just got to make sure the x's follow through. All right. So for some, this is already straightforward and you've done this multiple times. Just didn't maybe know that you can do the DNA to kind of simplify your process for you. And you probably went up to this number, 858, and were like, oh, God, it's a giant number. Now what do I do? So stop going up to the larger numbers. Keep numbers smaller. It'll do you good when you're going through the process here. Now we do group factoring. And I'm going to do it a specific way that most students will not do. That will identify what can come out of these groups before we actually take them out. Because there's a repetitive strategy here, and that repetitive strategy actually is easier to see when it's a single digit than when it's a bigger set of terms. So let's identify first the first parenthesis. We have a 3 and an x and a 3 and an x available to take apart. But before I take it to the front, I'm just going to take it to the front of each of these individual groupings. This is the best way to get the next point after. Here we've got a 26, and I believe 286 divided by 26 is 11. Cool. So we do have a 26 times x. That's fair. We can kind of just put a multiplication between them. But then this one is 26 times 11. All right. So why did I do it this way? Because now we can visually see some matching. Cool. These can be taken and written once in the front. And whatever is left over after we move them to the front stays in the parenthesis. So the x, which is not highlighted, minus the 11, which is not highlighted, stays. X, which is not highlighted, minus the 11, where it's not highlighted, stays. And then you've got the 3x that comes out to the front and the 26 that comes out to the front. All right. Muy bien. So let's rewrite this nicely. Now, this is where students are like, what do I do now? I don't see any matches. No one thing is matching with the other. I kind of maybe see something, but it doesn't look like a single 3x or a single 26. And what I tell you is, don't focus on them being single digits or even multiplication. Focus on copies and pastes. From this line, we basically copied two things and pasted it to a single. Twice. The 3x was copied to the outside, and a 26 was copied to the outside. It's like having the same file in two folders, and you're like, why do I have them in these both? I can just take them out of this folder and put them in the folder before it. Just one copy, so I know it's related to the other files. Well, we have the same thing happening, and most students will overlook a grouping that does the exact same thing. This is the final part that I'd say 70 to 80% of students really have a hard time seeing because we've done it with the single 3x and the 26. But when it starts to become a grouping, we're probably, or the students probably focusing over here, like, all right, well, they don't match anymore. What else do I do? Well, that's it. We have a grouping that we can match. So never limit yourself to the smaller piece because those are the easy ones. Now consider you're kind of upgrading your factoring knowledge. Not upgrading it with something new, but realizing that factoring doesn't just happen with small pieces. It can happen with copies that are much bigger. So like we did before, we take x minus 11 twice and just have a single version of it. And like the other ones, we start thinking about what's left over after we take out the x minus 11. Well, 3x plus 26. And that's the final piece to the puzzle. The rest actually will be super easy. Once we factored it, we got to think about where we came from. We came from the 0 that I stopped copying because it wasn't relative until now again. And this is the reason why we started factoring in the first place. That 0 gives us a particular product rule of multiple term groupings where if one is 0, it forces the other to be 0 and vice versa. So if I choose a number like 11 and make this 0, the whole grouping 0, then the multiplication of anything here is going to make that 0 and vice versa. So this sort of weird relationship between zeros and multiplications just gives us a very straightforward idea that, hey, at this point, we can just split this to a 0, and we can split this to a 0. Because now they can be isolated into their own parts. There's a bit more of a detail behind it, but this is kind of the shortest way to think about this. And this is why we want a 0 to be here at this point in time. When we actually did our 0, remember we had to move the number over to make it a 0. And this was because we didn't have a single power x anymore. We had a square. So as soon as we get that square, we're like, uh-oh, we got a factor. So let's get a 0. And then the 0 plays a part at the end. So some pieces get done early that we didn't see, and then some pieces that we did in the beginning now start to come back to finalize our problems. And what this means is we have two options for our answer. X equals 11 and x equals to 26 divided by 3. Negative 26 divided by 3. And then there's that sort of final choice. We have to go back to the problem and say, wait, what are we measuring? We can plug some stuff in the end and try and figure out the finale. But remember that we're basically measuring length. That's what we're trying to find as far as x is concerned. A length on an actual shape. And if we're going to go and get a ruler and start measuring stuff, we should never get a negative number. This is a case for entering realism, applicable nature of mathematics. You're never going to find a negative height. If you find a negative height, probably did some math issues, math problems. And I'm just guessing here, but you know, negative number will never represent the height of a building. So when we run into these cases where we're doing a real life problem and we're like, hey, I have two answers, which one is it? Oh, wait a second, this one's negative. I actually cannot have a negative length. So we automatically accept the positive number. 11's their answer. Kind of. Not quite, but almost there. Got to make sure we plug in 11 to each one of these x's. Got to be 33 minus 1, which is 32. So this side is 32, and this side is 9. That's the final answer. And we've defeated the Bowser mutated teacher, professor, demon. What's the word I'm thinking of? Demonization? The disfiguration? There's like a weird word for a very dysfunctionally mutated face. Anyway, that's it. So what turned out to be, again, we did basically a similar factor from the beginning when you saw what it was. I just tried to do a little bit neater. We started from this small section to this section And then we're like, uh-oh, we've got polynomials. Uh-oh, we've got weird numbers, AC method, group factoring, and finally getting your zeros. All right, I got it out of my head. There's a lot of little pieces in here that are very useful, very, very valuable. As far as not even just for this one problem, factor trees are very valuable to help you do problems much, much smoother with less error. Group factoring, very specific to a problem like this when we're trying to solve for a zero polynomial. But foiling, that was a very nice shortcut to kind of clarify. Make sure the foiling makes sense to you. If the other way with first, outer, inner, last works, do that too. That's fine. If it doesn't make sense, use this format. We're just combining every possible combination of four pieces. One of them is 3x, the second one is minus 1, the third one is x, and the last one's negative 2. And they're grouped in a specific way that we're not going to combine 3x and minus 1, right? That's a given. And then this little proportional factor here that started us off through the whole process, being able to understand where proportions take play in fractions, and even comparing a realistic aspect to a building that actually you can measure with your eyes and a couple of steps forward to a tree or some, heck, it doesn't have to be a tree. It can be a billboard. It can be something that you know the height of. And you're always able to find larger heights with smaller details around. Kind of like the scientific mind, being able to see the projection of the parabola when you throw the basketball into the hoop and being able to control just how much power you give that parabola so it makes it straight through and makes the science of everything. Anyway, I'm done nerding out. I'm gonna make another cup of coffee. Hope this was helpful. I'll probably, I like this as a standalone. So I might actually just upload this as a regular video in the end too. Yeah, we didn't go through a lot of different things, and I probably did I'll probably cut myself digressing right now, just talking and babbling because I'm supposed to press